Let's start from where we left off yesterday. So we had looked at what it means to differentiate vector fields which are tangential. So this you also saw in the other lecture, I imagine, uh, because derivatives of tangential vector fields need not be tangential. So you do an orthogonal projection, and that's the boxed definition here, onto the tangent space. So you actually get a derivative of something tangential, you get something tangential to the surface, and so we started noting down properties of the covariant derivative, and I will start by maybe proving the last line, so last property here, just so that this is how to use definitions, so just more familiar with them. And so let's do that. So you have two tangential vectors along the curve, and you want to look at, so the inner product of these two vector fields will give you a smooth function. So the prime there denotes the usual derivative, and on the other hand, uh, by definition, so this is the uh, derivative of this vector field along the curve. So that is a dot here. So without projecting onto the tangent space, yeah. And so this we already showed. So this we already studied the derivatives of vector fields along curves, and so now you simply plug in the definition for so you substitute, so you go back to the definition, so you have the x dot, the derivative of the vector field along the curve. So you want to replace this by x prime, so you take the normal factor to the other side and simply calculate it out, yeah? So you replace the x dot here by the x prime, so the derivative along the curve by the covariant derivative. So this gives you the added factor of the orthogonal projection along the tangent direction. So this will be that, and so of the normal along the curve, inner product with y, plus the second term would be, so x will remain as such, and for y you would do this. So you take the covariant derivative, you have the factor coming from the orthogonal projection, and so completely analogously to the other term. Now the point to note is x is so this here is tangential, so that was the assumption um, on the vector fields, right? So x and y were tangential vector fields, while this bit here is normal. So this is, so that term vanishes. So analogously for the other expression as well. So it will leave you with what you desire. Yeah? So this is just x prime with y, the covariant derivative, paired up with the tangential vector field there, and just merely using definitions. Yeah? So um, I think I mentioned this yesterday, so let me mention it again. So, and this is sort of an important point of view as to, especially when you're looking at the hypersurface situation, because you always have an ambient space. So you're not studying the object by itself. So you are looking at an ambient space inside which this sits. So you always have to worry about which uh, what quantities are dependent only on the surface, or what quantities depend on the way the surface sits inside the ambient space. So that's the main concern when you do geometry in the fashion that we are looking at. So your hypersurface, so your situation is of a hypersurface sitting inside a regular hypersurface sitting inside Euclidean space, and so and from that point of view, so it's important to note that the so we'll come to this perhaps tomorrow. Um, so therefore, I'll mention it now. So when we go back to it, you can see that this is so. It's not merely a heuristic. So for now, it's just a heuristic of what happens, because so what the covariant derivative of a vector field along a curve does is it ignores the normal component. So so that is the secondary part, because the normal component is in some way measuring how your hypersurface sits inside the Euclidean space. Yeah. So it's of x. So so when I say normal component, I mean component of x which is normal to the surface, um, and measures the rate of change along the curve, but as viewed from the surface, and that's the crucial bit here. Yeah. So this feature you will see time and again, of what something is to be viewed from your surface without any reference to the ambient space. Yeah. So so this is in perhaps the first true quantity that you're looking at where this is so. Um, so what does I want to say? So the rate of change of the vector field along the curve as viewed from the surface itself. So that is just common language to say something which we will see later about whether something is intrinsic. Yeah. So this is to mean uh, perhaps I'll put a perhaps here, not dependent on the way the surface sits inside Rn plus 1. I will throw in the word intrinsic here. So, so heuristically speaking, this is what one means by saying something is intrinsic. So how something appears from, so there exists nothing else, right? So there is no ambient space, etc. If you're only looking at this, so the normal component does not exist for you, then yeah. So this is a suggestion that perhaps the covariant derivative is something which is intrinsic to the surface. Yeah. Perhaps you have seen this already. You must have, because all Weingarten and so on you have seen. So is this notion of so perhaps I write it down. It's best written down. So you have so smooth vector field, which is so along a curve. Um, so along an n surface. So meaning tangential when I say along an n surface in Rn plus 1, and you take a curve smooth curve into the, I mean, on the surface. So this is a curve in the surface. Now, maybe I should give it a different name. So maybe x tilde. So then x tilde, this already we saw along gamma by simply composition. Yeah. So we said one example of looking at vector fields along a curve is actually given by just restricting the given vector field to the curve. So, so and of course, all this along simply means that you're not necessarily tangential to the surface. Yeah. So it is only tangential into the ambient space. So that's all you're saying. So there is no p here. What is this gamma t for every t in the interval? So all this we saw. So now the differentiation of vector fields along a curve is the directional derivative in the tangent direction. Yeah, so that is the observation. So I imagine you have already seen this in terms of covariant derivatives of because when we are saying covariant derivatives, we are looking at it in a very special sense, only in the direction of along a curve. But of course, you can look at covariant derivatives of vector fields with respect to other vector fields. Perhaps you have seen this with respect to other tangent vectors, but more generally, you can view this as with respect to other vector fields. So what I want to say is, so differentiation of vector fields along a parameterized curve. So this is the x dot that we had, is the directional derivative. After all, covariant derivative is just a generalization of this directional derivative. Of course, for which I have to say what directional derivative is on a surface, but so in the tangent direction. So this you have already seen what covariant derivative is. So in the tangent direction, and all that, just to say, that is, the symbols make it very clear what I'm trying to say. So the differentiation along gamma is the x dot. What is the directional derivative? So in the tangent direction, meaning the velocity vector field is a tangent vector field. So at that point, you look at the derivative of this original vector field, right? So because x was just the x tilde viewed only along the curve, restricted to the curve, right? So that's the relation between a vector field along a surface. It's the you look at the restriction of this vector field to the curve, then you look at the derivative with respect just along the curve, that is x dot. So this is the same as looking at the full vector field, not restricting to the curve, and taking its covariant derivative with respect to the velocity vector field. Yeah? Velocity vector field, of course, is tangential. So, okay, so that's sort of a remark I wanted to make. So maybe here instead of directional, so I could write covariant. So I don't know, maybe you saw nabla instead of d. So sometimes. Okay, so since we, yeah, so this is of course relevant for us, I suppose. So you look at a curve on the surface. So this is a geodesic on the surface if and only if its covariant acceleration is 0 along the curve. So what is covariant acceleration? So this is x dot prime. bracket if you want. So this is 0, of course, along gamma. So this perhaps I will point out a y. So you have to pause a little bit to think why this is so. So you just have to use definition, right? So on one hand, what geodesic is, on the other hand, what covariant acceleration is, and related to the, how prime and dot are related, yeah, as derivatives. So that's the key part. And noticing, of course, that the velocity vector field is always tangential. Yeah? So those are the points that you need in order to look at this equivalence. So in fact, one way of defining what geodesics are is actually by this equivalent, by looking at the covariant derivative. Yeah, so very often that's how geodesics are even defined. One crucial notion which covariant differentiation along curves gives us is the notion of parallelism. On the surface. So it is broader than what I will say here. Um, so so this is just true when I say something is parallel. It simply means its covariant derivative is actually 0. So but here we'll take a very specific geometric view. So covariant. So this leads to the notion of parallelism on hypersurface. Yeah. So first, let's look at what the situation is in the Euclidean case. So this already is very suggestive. So you take a vector. So recall that a vector is for us a point and vector in the tangent space of the point. Because this you canonically identify with Rn plus 1 itself. So maybe I take two vectors here. So I take, let's say, W is some QW. This is tangent at some other point, yeah, in the tangent space to Rn plus 1 at another point. So we say that these two vectors are Euclidean parallel if V equal to W. So here, of course, draw a picture. Right. So recall, of course, that the so a priori there is no particular relation between tangent spaces at different points. Right. So the reason for such a definition here is, of course, the second. So V in the vector V varies over all vectors in Rn plus 1 as is the case in W. So it makes sense to talk of V being equal to W as points in Rn plus 1. Yeah? So okay. Now, and this of course is the usual parallel, right? So you take a vector which starts at P and goes to Q, you say, and goes to V, and you, which means by itself it's just the translate of the vector V starting at 0. And similarly for Q, right? So, and so if you say that V is W, these two arrows are parallel, right? So that is they are the same if P is equal to Q. So we haven't ruled that out here. But even if P is distinct from Q, they are actually parallel as if you draw a picture. Yeah. So okay. So now we are interested in vector fields along curves. So again, only in Rn plus 1 so far. Yeah? So vector field along curve. So when I say curve, it's always parameterized. Yeah. So if it's one, we fix the parameterization. This Euclidean parallel. Because everything happens in Euclidean space. That's why the addition of Euclidean everywhere. If what happens, it's pretty much the applying the above definition to this vector field. So x of t1 is x of t2 for all t1, t2 in the interval, right? So this vector field along a curve means that xt1 is something in the tangent space at gamma t. Okay, so maybe I should write that. So where xt is gamma t comma xt. So this x without the arrow is the function associated to the vector field, right? So, and in general, we don't necessarily make a distinction between these two. And this case, you can draw a very easy picture. Yeah. So again, the second Euclidean parallel also you should draw a picture. So it's just some curve, and you have the along the curve you have all these little arrows lying parallel to each other. Yeah? So that's all this. So if you draw it pictorially. So from this, what you see, so the definition of Euclidean parallel of a vector field along a curve. So this immediately forces that a vector field along curve is Euclidean parallel along gamma. So x is along gamma. So this is if and only if x dot is actually 0. Why? After all, that's what it measures, right? So it's not changing. So you're saying it's parallel if at every time t, x of t is the same. So there is no change. So when you differentiate, you're going to get 0. So as you change t, this is really not changing. So parallel really means is equivalent in the Euclidean case to the derivative along the curve being 0. Now we can wonder about what happens if you look at the covariant derivative on a surface. Yeah? So this is just Euclidean everything. So we now go to the hypersurface case and wonder what happens with the covariant derivative. So given an n surface S, in Rn plus 1, and gamma I to S parameterized curve. So we take a vector field which is now tangent to S along gamma. So it's a smooth vector field tangent to the surface along the curve. So this you call is Levi-Civita parallel. So the reason for this is so Levi-Civita is so the connection which you have on these sort of these Riemannian manifolds is what is called the Levi-Civita connection. And so in other words, the associated derivative, covariant derivative. So when you have a connection, you can differentiate. So that's called Levi-Civita. So the nabla that you write. Yeah. So you write like this. No. So either x, y, or sometimes you write something like this. So this here is called the Levi-Civita connection. So, and so all I'm trying to say is this parallel is simply that the covariant derivative is 0, and with respect to the Levi-Civita connection, and therefore we call this Levi-Civita parallel. If the covariant derivative along the curve is 0. In other words, so this is again repeating what I said, but rephrasing what I said in the context of the remark I made here about something being intrinsic, possibly. Yeah. So, how it is when viewed from S. So, the fact that the covariant derivative along the curve is 0 does not mean that there is no change in the vector field at all. All that it means that there is no change in the vector field along the surface. So, or as viewed from the surface. Yeah. So that is what it tells us. So I'll write that again just to emphasize this point. So we say that vector field, tangential vector field is along the curve is parallel along the curve if this is a constant vector field along gamma. Yeah. So and the key detail being here is as viewed from S. Yeah. So it is not necessary that it is actually constant. So maybe there is a whole normal vector flow which is going, yeah, which is non-trivial. However, when you only live on the surface, you don't perceive that. So you only perceive this, and so along gamma, as seen from the surface. So that I want to mention. So we will note down some important properties of this Levi-Civita parallelism. And we will immediately put them to use. So pretty much every property I will list, we will use immediately after we list the properties. So let's say parallelism. So if your vector field, so everything is as before, right? So the setup is always this here. The setup is always that, where your vector field is tangent, yeah, along the curve. So this is parallel along gamma implies that, so we just saw that it's parallel along gamma if the here if the covariant derivative Levi-Civita parallel, right? So covariant derivative is 0. So in other words, this is saying parallel along gamma, meaning that the covariant derivative is 0. This is the same as it has. This implies that the vector field has constant length. So the calculation is very much like how we showed that geodesics have constant speed. So this is exactly that calculation, just applied in this context. So you look at, of course, x here is x of t is a function of time. Yeah. So what is this? So this is d by dt of the inner product of x with itself at every time t. And this is, of course, so I'll put twice because of symmetry. So this is x. But what can you say about the inner product of x and x prime here? Because we know it is parallel, so x prime is 0, so this is 0. So meaning that the length does not change, yeah, with time. Now, similar computation, if you take two vector fields which are parallel along the curve gamma, so parallel vector fields, along gamma. So this implies that, maybe I write these proofs in brackets. So this implies that the inner product is actually constant along the curve. Is constant along the curve. Of course, this is again, so the properties of the covariant derivative that we listed. So all you have to do is you look at this. Yes, we want to say it's constant, so you want to take its uh, derivative. So here it's just the usual derivative, right? So inner product gives you a function. So this, of course, we saw by the properties. This is x prime y plus xy prime, and both of them are 0 because both x and y are parallel along gamma. So x prime is 0, y prime is 0, so their inner product with any other vector is 0, and we are done. So that is the other property. So again, under the assumption that x and y are parallel along gamma, then the angle between x and y is actually constant along gamma. So angle, so I hesitate to write this, but okay, this is okay. Um, so the of norm of x, norm of y is constant along gamma. Again, this is once you have proved all the others, so you've just proved that the inner product is constant along gamma. You've proved that the norm is constant along gamma. So every factor in the argument is constant along gamma, and therefore the angle is also constant along gamma. Yeah, so that needs no separate proofs in this sense. And so if you so the vectors parallel along a curve, these really form a vector space, because sum of two such uh, derivative of the sum of two such things is so this is additive. In other words, it's a linear map, and scalars don't matter. Yeah, so maybe I write that. So parallel along gamma implies this, of course, implies x plus y. So let us apply this to our velocity vector field of the curve gamma. The velocity vector field gamma dot is parallel along gamma. So this is equivalent to saying what we saw. that the this is a definition, right? So the tangent vector field is gamma dot. So parallel means that the covariant derivative along gamma is zero. But then what is this? So this is the definition of prime. Apply that. So this gives you inner product here. Let me think. So already I have a dot. So I will have, of course, the acceleration here. So and this would be paired with, so gamma prime. What was this? Gamma prime. So this is the normal vector field along the curve times, and this is 0. So you can equate these two sides. So I will leave that step. So if and only if the acceleration is normal to the surface. So this, of course, gamma is a geodesic. You've seen that the velocity vector field is parallel along the curve, if and only if it's a geodesic. So let's look at the so a couple of results here. So I'll merely indicate proofs here. So two results of interest. One, and this will actually give rise to parallelism or parallel transport. So setting is usual. So S n surface in Rn plus 1. I take a curve gamma, a parameterized curve on the surface. So this is pretty much like geodesics. So suppose you take a point time t in the interval, and you take a vector v in the tangent space at gamma t, gamma t naught. So you've chosen the t naught. Take a vector in the tangent space to the surface at gamma t naught. Then there is a unique vector field which is parallel to S along the curve. So then there exists a unique um, vector field, vector field V, which is tangent to the surface along, so tangent to the surface along the curve, which is parallel and of course the initial vector which you are given is attained at some point. So t naught. So I'll merely indicate the nature of the proof, and this is just to realize that, doing similar computations over and over again is how you master definitions and properties that are there. So of course when you talk of something exists uniquely, so on. You suspect there is always a differential equation around the corner, and that's going to be the case here too. So I simply write down the definition first. So all along the curve, of course. So covariant derivative along the curve. Now, what I do again, so it's the trick we did before. Sorry, here v dot. So that derivative along the curve we replaced by the covariant derivative. So exactly as we did above. So this we will change then to covariant derivative, and there will be a correction term, right? So this will be the covariant derivative minus is still okay. Yeah. So this is v n comma prime minus, or is it a plus? This is that minus this. So I think it is okay with the minus and the minus. So we paired with the derivative along the curve of the normal. So there is a normal here. So this is now, of course, this just quickly simplifies. So which term vanishes here? The first term, right? The second term. Where is the derivative? Yeah, the first term. So where the derivative, because the covariant derivative is tangential, right? So when you pair it to the normal, that vanishes. So you're left with and so okay. So why is all of this rewriting useful? Simply because now you can say so. So this such a vector is parallel. So in other words, its covariant derivative is zero. If and only if the right hand side is zero, and the right hand side for you, if you write this in coordinates, is first order differential. Oh, I forgot the vector field here. Sorry. So mm, there is of course the derivative here along the curve, and so the normal vector. So this is zero. So this you just observe is system of first order ODEs. So and so existence and uniqueness as usual gives us what we want, except, and this is of course the game you have to play all the time. So existence and uniqueness theorem for such systems. When I say such systems, I mean system of ODEs. Gives us that there is a unique vector field along the curve and satisfying the equation. So it's a solution. So there is a solution which is unique, satisfying the equation with the initial condition. With the initial condition, satisfying equation with the initial condition that the at time t naught you get the vector that you started out with. So okay, so far it's just restating your that something is parallel in terms of getting a differential equations of the system of differential equations from it, uh, and using this. However, notice that you want a solution which is tangent to the surface. So that remains to be shown, right? So that such solution is actually tangential. So remains to show. So in all of this being tangential, so anything to do with derivatives, you lose that it is tangential. Yeah. So even though the original vector field may be tangential, when you take its covariant derivative, you lose that feature. So so when you take the derivative along the curve, you lose that feature. So it remains to show that V is actually tangent to S along gamma. So again, this is just a little bit of work. I'm just wondering if I should do this or not. Uh, but this is usually the important point, right? In all of these proofs, uh, the fact that a differential equation is around the corner is just writing out expressions. But so what we want to show is that this v is actually tangent. So I pair it with the normal vector. I take its derivative. So the idea being that this derivative will turn out to be zero. This is of course the usual derivative on the interval, and that this turns out to be zero would mean that it is constant, and then we will see that at some point that this constant is zero itself. So that's the idea. So that's why we take the derivative and not just the pairing between this. So so we just use everything that we know concerning this. So I'll quickly compute. So this is the first derivative. So then it's the derivative there in the other coordinate. This is along the curve. So derivative along the curve. Now this again I get my v prime in terms. So what should I substitute here? So I do want the composition with n to remain intact. So what I can substitute is, I suppose, v dot in the first one. So this is minus, what is this pairing? So this is v, the normal field along gamma. So this is the normal along gamma and the normal. So that's the first term. And the second term, I keep it as such. Now in the first one, I just use, so pull out the constant. So, and then I have the normal vector. So that is unit normal. So that becomes 1. So you're left with just, sorry, this is just the derivative of this vector field. Um, oh, and plus the same thing. Oh, I see. So this just pops out to be 0. Comma, the derivative here of that, and this is 0. So what we have shown that is this is constant along the curve. So that is the pairing of the vector field with the normal along the curve is constant along the curve. So now if you can show that this what this constant is by getting it at some specific point, then we are done. But then this is what we have, and since at t naught what happens? So I look at the pairing at t naught. So that is the, but v of t naught is the little vector v, and the normal will remain that. But the little vector v was chosen so that this was tangential, right? So something in the tangent space at gamma t. So paired with the normal, this is 0. So why is this? Since this is how we chose our v. Yeah? So v is in t gamma t naught of that s. And since this is 0, the constant must be 0. So that is, so this constant being 0 means that the, that is v is orthogonal to the normal, so it's tangential. So in all of this, that's often the interesting part, where you use information that you know about the vector field of the curve and so on. Um, the other things just directly you get from differential equations, right? So you're just going to cite that. Okay, so now what is the idea? So once you have this result, what you can do is you can immediately get to parallel transport. Sorry, because what does this give us? So this gives us a certain uniqueness as well. So given a surface and the curve on the surface, fixing a point and a direction in the tangent space of the point, you get a unique vector field which is tangent to the surface along the curve and is parallel. Yeah? With the initial, I mean, velocity, initial speed being, velocity being the given vector. Yeah. So initial here meaning t0, right, at some point. So it's not necessarily 0 here, but so the uniqueness will actually define a map for us, and this will give us parallel transport. So, so you can use this Levi-Civita parallelism, um, leads us to transport tangent vectors from one point to another, right? So that is a spectacular thing if you think of it. To why? Because a priori these tangent space at two distinct points are disjoint sets, right? So if you think of them as p comma v and q comma v, right? Even if you're because p is not q, this can never be the same, right? So tangent vectors at distinct points are disjoint, and yet you can somehow move along from one vector in a tangent space to some vector in another tangent space. Yeah? So it's quite a remarkable thing, and so tangent vectors from well, so I simply we lose and say from one point to another, meaning tangent vector in the tangent space at one point to another. So we need the mild. So far we've just looked at intervals, which so we have never looked at curves going from one point to another. So this is what we want. So towards that, we look at take 2 points. So PQ on the surface. Um, so a curve in the on the surface from P to Q. So a curve on S from P to Q parameterized curve. Yeah, so is a smooth map. So notice that we are taking closed intervals because at the end points we want P, and at one left end point we want P, at the right end point we want Q. So with so that's what you mean by joining 2 points, right? So with gamma A is P, gamma B is Q. So one point which I addressed very briefly already once is on subsets which are not necessarily open. So the derivative is defined by taking local smooth extensions. Yeah. So you say that from this closed interval, for example, right? So I'll just stick to this example. So gamma as above is smooth if it exists to if it extends if it extends to a smooth where from so let's say if it extends to say infinity at gamma tilde from some open interval in R which contains AB. So AB is contained in this I, and this is open in R. And extension meaning that if you restrict that to the original interval, you get back the original curve, right? So that is that. You can actually check that this definition coincides with the existence of one-sided derivatives, right? Typically on intervals, this is what you see, right? So okay, so there is the interval is closed, so you look at the derivative from the right at A, from the left at B, and so on. It is a nice little exercise to see that this extension into, so if you give me a one-sided derivative, I'll write you an extension. Conversely, if there is an extension, then of course you very well have the one-sided derivatives. So perhaps another important point to notice in this is that you see this curve gamma tilde is far from unique, right? So there is no uniqueness in this local smooth extensions, and so it is useful to say that the curve is smooth, but you can't say anything about its derivative, right? Because the smooth extensions are not unique, so you can't simply define that the derivative of gamma is the same as derivative of gamma tilde, because I could take another extension gamma double tilde, and then its derivative at these points may be different. So however, one can see that when things are sufficiently nice, let's say convex, so whenever you can have something like path connectedness, you can go through small segments which are smooth, then you can actually define the derivative of a map defined on a non-open set to be the derivative of any local smooth extension, because they all coincide under mild hypothesis. So but you can give examples where it does not. Yeah, so if you can hook this up. So I just wanted to make the point, because so typically one doesn't see differentiation on sets which are not necessarily open in calculus analysis courses. So it becomes necessary in topology and geometry. Yeah, so not that it is not necessary in analysis, but I'm saying that it's apparent that you need these things. So now, okay, once you have so you know what it means for a curve to join 2 points, smooth curve. So you look at curves which are so you take a parallel curve from between the points from P to Q, and this determines a map between the tangent spaces. After all, that is what you wanted, right? So you take a curve from P to Q, then you have a map. So P gamma from the tangent space at P to the tangent space at Q. How is it defined? Defined by, so what is the action of P gamma on a tangent vector at P to the surface? So given your gamma and given points P and Q, so you have that Q is gamma of some T naught, right? So you're given a T naught in this interval I, then you are given a vector V here, and by the theorem, there is a unique tangential vector field which is parallel along the curve, such that v of p is or you know is v at the vector field capital V at p is actually the tangent vector v that you started out with. So this because of uniqueness, you can define this map, right? There is only one v which does the job, and its value at b, which is what will give you q, right? So you can just define this as a map. So because otherwise there are uniqueness is what guarantees that it's a map at all, right? So you have well definedness. So where what is this? So where for v in TPS um, is the unique parallel vector field tangential to the surface. So tangent to the surface along gamma given by the theorem. So meaning along gamma such that v of a is the vector v that you started out with. Then you look at whatever the images at b, you define this to be the map. And this is called parallel transport. So this map here, so that is called, so parallel transport of v along the curve along gamma to the point q. So of course clearly it's a linear map, yeah. So it's a linear map between the tangent spaces.